Hi, everyone. Today I'm honored to share our paper, Hierarchical Semantic Correspondence Networks for Video Paragraph Grounding. To begin with, I'm going to summarize the highlights of this work for preview. First, we investigate how to exploit the hierarchical visual textual correspondence behind the task of video paragraph grounding, VPG. To the best of our knowledge, this is the first time that hierarchical visual textual correspondence is explored and multiple levels of linguistic queries can be grounded in VPG. Second, motivated by the inherent hierarchies of videos and paragraphs, we naturally introduce a pioneering hierarchical modeling paradigm without using external components such as object detectors. Third, we design a novel encoder-decoder network to explicitly learn hierarchical cross-modal alignment and utilize dense multi-level supervision. Fourth, the model achieves new state-of-the-arts and shows a series of hierarchical perception capabilities for cross-modal semantic association. Next, let's continue with a little bit more backgrounds. We focus on the task of video paragraph grounding, which is to localize the timestamps of multiple visual events from an untrimmed video at once, where each of the visual events semantically corresponds to one of the sentences in the given paragraph description. To well address this problem, the key challenge lies on how to understand the content of a complicated paragraph and an untrimmed videos as well as the complex semantic relations. Before diving into method details, I want to spend some time talking about what motivated us to conduct this work. In the task of VPG, prior works often model the video-text relations from a single sentence level. They neglect the rich cross-modal relations at other semantic levels, hence failing to benefit from the hierarchical learning. We observe there naturally exist two perspectives of hierarchies in terms of cross-modal correspondence. On the language side, the linguistic semantics of the paragraph can be decomposed into three levels including words, sentences, and paragraph from the bottom up. On the video side, the temporal granularity of visual counterparts is presented as a coarse-to-fine hierarchy with nested temporal dependencies. Motivated by the observations, we model the three-level bottom-up semantic encoding process of the language hierarchy by a hierarchical multimodal encoder, and we model the three-level coarse-to-fine temporal decoding process by a hierarchical progressive decoder. Here is the framework illustration of the proposed hierarchical semantic correspondence network architecture. On the whole, the model is composed of two parts, namely the hierarchical multimodal encoder and the hierarchical progressive decoder. They both comprise three levels of encoders or decoders. The visual features and textual features are flowing down the visual path and textual path, interacting with each other via different levels of multimodal self-attention layers of the encoders. Before being fed to the next level, textual features will be pooled and aggregated into the next level's representation. The encoded visual features are then fused into the textual features. From the paragraph level down to the sentence level, and to the word level, each level of decoder will utilize a conditional LSTM to absorb the contextual knowledge from the higher level, and then try to decode the temporal locations at a finer level. At last, we employ a cross-attention module to fuse multiple levels of semantics to perform the final grounding prediction. The training objectives of our model are presented as below. In total, we have an encoder loss, a decoder loss and a grounding loss to train with. The encoder loss consists of three terms, respectively corresponding to the video word alignment, video sentence alignment, and video paragraph alignment learning. The decoder loss consists of four terms, including the decoding loss to regress the paragraph level and sentence level timestamps with their ground truth, and two weakly supervised decoding loss to enable the word level learning. We also adopt the grounding loss to regress the final predictions derived from multi-level semantics. We compare the performance of HSCNet with the state-of-the-art grounding methods. It can be seen that HSCNet significantly outperforms all the competitors. Specifically, we observe that our hierarchical model is more advantageous in the TACOS dataset, which is featured by its longer videos and denser sentences in the paragraph. Next, we present the first ablation experiment, which is on the impact of different modeling levels. Results are shown in the table. Firstly, we observe that converting the multi-level model into a single sentence-level model leads to a significant performance degradation. Secondly, each modeling level is important for accurate grounding and complements well to each other. We also conduct ablation studies on the impact of different cross-modal alignment loss. We can see that employing each loss can consistently bring improvements, and the word-level cross-modal alignment has the greatest impact on the performance, since it injects the lowest level details into the model. The last experiment is about the effectiveness of different levels of decoders. We regard the variant with only sentence decoder as baseline model. It's clear that decoding the temporal timestamps at more levels can facilitate the localization learning and hence improve the performance. We visualize the predicted timestamps by the model for different levels of queries, as shown on the right side below. As is demonstrated, the model is able to give reasonable results for a long untrimmed video with frames of similar visual appearances and subtle action variations. In terms of paragraph level and sentence level understanding, the model gives an accurate paragraph timestamp and predicts a series of sentence timestamps reasonably ordered within the timespan of the paragraph. This reveals the model's capability to perceive the in-level and cross-level context. In terms of the word-level understanding, we observe many success cases. For instance, the verbs, peels, and chops, are grounded by 2 moments close to the action durations and ordered in a correct relation. Nevertheless, we also notice there are still many failure cases due to the limited amount of training data and weak supervisory signal. In the end, we summarize the conclusions as 3 points. We propose a novel HSC net, which is designed as a hierarchical encoder-decoder architecture to learn and exploit the multi-level visual textual correspondence. We show that the combination of the encoder and decoder enables the system to learn fine-grained hierarchical cross-modal understanding capabilities for grounding. The proposed HSC net establishes new state-of-the-arts on 2 challenging benchmarks. Thanks for your watching and listening.